Okay, let's continue. So integers are countably infinite. What else is countably infinite? Well, sets like this. You have the Cartesian product of natural numbers with itself. So n cross n, which is the set of pairs of natural numbers, right? This set is countable. And if you want to know why, I have a way to count the elements of the set. So let's say we have n1 here and n2 here. So 1, 2, 3, 4, etc. 1, 2, 3, 4, etc. So we have 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, and 4, 1, 4, 2, 4, 3, 4, 4. And if you write it like this, as a huge matrix or a table, how can you count the elements of the set, like 1, 2, 3, 4? Yeah, would you like to say something? Diagonal way, right? Start from here, right? This is the first element. Go to here. This is the second. Maybe this is the third. This is the fourth, fifth, sixth, and then seventh, eighth, ninth, 10th, etc., etc., right? In a diagonal way. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., etc. That's a way to count the elements of this. So this is also a countably infinite set. And similarly, so if you have a countably infinite set A and a natural number n, A to n, which is like A cross dot 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 A n times, is countably infinite. You can check this in a similar way. Is countably infinite. So if A is a countably infinite set, this A to power n is countably infinite. What else is countably infinite? Q, the set of all rational numbers. A, B are integers, and B is non-zero. Is countably infinite. Okay. Anybody sees why? So it is just like z cross z, right? You can, but you need to skip some elements because you don't want b to be 0. But you can see q as a subset of z square. And since q can be seen as a subset of z square, and z square is countably infinite, q must be either finite or countably infinite. And we all know that q is not a finite set, so it must be countably infinite. So this is also a countably infinite set. Because we can see it as a subset of z squared. What is not countably infinite or countable is the real numbers and also irrational numbers. These are uncountable. That is, they are infinite but not countably infinite. So this is kind of the definition of being uncountable. So we have our classification of sets. There are finite sets, countably infinite sets, and uncountable sets. And sometimes we call finite or countably infinite countable, just countable. So, well, finite sets are finite, right? For countably infinite sets, we have n, z, z squared, q, etc. For uncountable sets, we have r, r minus q irrationals. For instance, the interval 0, 1 is uncountable. Interval 0, 1 is uncountable. Why? Because there are so many irrationals in it, right? There are so many irrationals in it. And because of those irrationals, this set is also uncountable. So if you take the course IE 500, you will have actually a chapter on countability. So that's why I don't want to spend too much time on this issue. But I just want you to know that irrationals are uncountable. This set, the interval 0, 1 is uncountable. But rationals, integers, naturals are countable sets. Okay? That's all I want to say. Okay. Well, what were we talking about? What were we talking about before this discussion? Random experiments, right? Sample spaces. So let's keep giving examples of sample spaces. Well, this is going to be an uncountable sample space. So another example, motion on a line. So you have a line, okay, and you have somebody, maybe a bee, an insect, moving randomly on this line. So let the bee move on the line for an hour. So where does it stand when you're back? So if this is what you're interested in, this means you're interested in the position of the bee at the end of an hour. So your outcome is the position of the bee at the end of an hour. So what is our sample space? Just the real numbers, right? It can be anywhere on the line. There is no restriction. Well, even if you know, maybe let's say this is the starting point. Let's say you know it. Let's say it is x or just 0. Let's say it's just 0. Still, it's a random movement. So at the end of an hour, maybe the bee was very fast. Well, you can say that it cannot go too much. It cannot maybe have like 5 kilometers, but still, you don't want to exclude. Again, the sample space is the set of all possible outcomes. So don't exclude the outcomes that are not very likely. Okay? That's what we don't want to do. We would like to have a sample space that is as rich as possible, as realistic as possible. That's why. But we don't include, for instance, minus infinity and the plus infinity. We don't do that. That is not really a possibility in real life. So So that's an uncountable set. And finally, I'd like to give examples about coin tossing. Problems about coin tossing are always nice, simple looking, and also interesting, especially when you have an infinite number of coin tosses. So, toss one coin, or toss a coin once. Toss a coin once means that you will see heads or tails, right? So you can choose your sample space as heads or tails. You don't have to. You can say, well, H is replaced with 1 and tails is replaced with 0. So there is nothing wrong with that. As long as you know what this means. 1 means H, and 0 means tails. As long as you give this explanation, it is fine. Another example is maybe plus and minus 1. So when you get heads, you can see this as like gaining 1 lira. And when you get tails, you can see this as losing 1 lira. So you can already define your sample space as plus and minus 1. So this is fine. Well, if you toss a coin 5 times, this sample space will not be suitable for your analysis, for your modeling. You have to define a better sample space because you have the results of 5 tosses. Heads, 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 all the way down to all tails, right? How many possibilities do you have? 32, yeah? So how should we define our sample space? First of all, what is an outcome? Well, in an outcome, we want to make this rich, right? So we need to keep track of the results of every single toss. So I want the result of the first toss up to the 5th toss, where these symbols, omega i's, are, let's say, H or T for each I. This is my outcome. Well, as a set of all possible outcomes, this is my sample space. Here, there is no assumption about flipping the coin independently. I don't say anything like that. Maybe the coin is biased. Maybe the result of the first toss somehow affects the result of the second toss. This is all fine. We're not assigning probabilities yet. Okay? This is still a nice sample space for this experiment. So what is this now? What is this? This is a finite sequence of 5 things, right? Finite sequence, or a 5 tuple. Right. So this set is finite for sure. This set is also finite. You even told me that the size of the set, okay, this means cardinality, is 2 to 5, which is 33. So let's pass to the infinite example. Toss a coin forever. Toss a coin forever. Now, what is your outcome? What is your outcome? For instance, I toss the coin. I get heads, heads, tails, 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 heads, and it goes on forever. There is no end to that, because I never end the game. So that's why my outcome is an infinite sequence. Okay? And this is not a very mathematical way to write it. So that's why we're introducing this notation, omega 1, omega 2, etc. You can also write it as omega n indexed by n, right? Where each omega I is, again, either heads or tails. For each. Now I write for each I in n, because I have 1, 2, 3, 4, my indices. So this is my sample space. So is this point clear? Is this expression clear for you, for everybody? So this is a sequence. This is a sequence. So whenever we say sequence, it means an infinite sequence. We don't need to say that it is an infinite sequence. So a sequence is just a bunch of numbers indexed by natural numbers, right? So you just have 1, 2, 3, 4. That's a sequence. So it's a set of sequences. An outcome is a sequence. The sample space is the set of all sequences in this form. It's an infinite set for sure. It's an infinite set for sure. But is this countable or uncountable? Who wants to say countable? This really looks like a countable set. Who thinks it is uncountable? Nobody? So you guys are just indifferent? Well, it is an uncountable set. It is very surprising, but maybe not surprising to some of you, but to me it was surprising when I first saw this result. So that's an uncountable set. Okay. And before we finish the discussion of this coin tosses, so you see this set is 1, 0, right? You can see this set is you can see this set as 1, 0 raised to power 5, right? Cartesian product of this set by itself 5 times. And this you can see as 1, 0 cross 1, 0 cross 1, 0, etc., etc. And sometimes we write it as this: 1, 0 raised to power natural numbers. And this means the set of all functions from natural numbers to 1, 0. Set of all functions from natural numbers to 1, 0. Indeed, the outcomes are functions from natural numbers to 1, 0. Natural numbers to 1, 0. This is 1, 0, this is 1, 0, this is 1, 0. So this is like an infinite Cartesian product. It's an infinite Cartesian product. So a set of all functions from naturals to 1, 0. In other words, set of all sequences whose members are 1 or 0. Of course, you're welcome to prove or try to see why this set is uncountable, but this is not something that I'd like to discuss in the lecture. Okay? It's an interesting fact. Interesting fact. So the main message of discussing this result is that even if you're in a very simple setting of coin tossing, you easily get into uncountable sets that are crazy. Countable sets, they're still okay. But just in the setting of coin tossing, you end up with an uncountable set, which is not very nice, not very elementary, right? Not like a 250 thing, math 250 thing. So you really need some mathematical machinery to be able to deal with those structures, those examples. So even in the setting of coin tossing, you need some nice mathematics to deal with this, okay? Because that's an uncountable sample space. So that's why we need mathematical machinery. We will discuss the mathematical machinery coming from measure theory, okay? Okay, so these are some examples of sample spaces. So we've seen that sample spaces can be finite, countably infinite, or uncountable. So now what is next? What is the next thing that we should discuss? What is the very simple term from probability that you remember? You calculate probabilities of what?
Random variables, events.
Events first, random variables later. Okay, events. So we discussed random experiments. Now we will discuss events. So informally speaking, an event is a statement about a random experiment whose truth is determined once the experiment is performed. So maybe in the setting of throwing a die, for instance, the statement that I get a prime number on the face is an event. I get a prime number, or I get an odd number, I get an even number. So these are all statements about this random experiment of throwing a die, but you cannot tell me if the statement holds true or not before you perform the experiment. You have to see the result, the outcome of the experiment to be able to tell if the statement holds true for the random experiment. So you need to see, you need to wait and see. So you need to know the outcome of the experiment. Then, in the setting of mathematics, or more formally, an event can be defined as the set of all outcomes in the sample space for which the statement holds true. So in the informal version, an event is just a statement. In the formal version, it is a set of outcomes for which that statement you're talking about holds true. But mathematically, an event is a subset of the sample space. So if you have a set A that is a subset of omega, this is your sample space. This is your event. And this is my subset sign with this equality part. Okay? So when I want to say subset, I use this. When it is a strict subset, meaning that it is a subset but not equal to the set here, I use this sign. In other words, if you perform the experiment, for each of the outcomes, or when you see the outcome, you can tell if the event, if the statement that you're talking about occurred or not. Look at the outcome. Check if omega is in A. So let's say you have an event A, okay? So how are we going to decide if the event occurred or not? Perform the experiment, look at the outcome. Let's say it is omega. Now check if omega is an element of the set A. Because formally or mathematically, A is a subset of the sample space. So if you know omega, you should be able to tell me if it is an element of A or not. So if omega is in A, we say that A has occurred. If omega is not in A, that is, if omega is in A complement, which is omega minus A, this is the set difference, right? We say that A has not occurred. So you have your sample space, and this is your world, right? This is your world. And this event partitions your world into two parts, A and not A. This is the whole world. Let me just draw it clearly and carefully. So this is the whole world. This is a set of all possible outcomes. If your omega is here, this event occurs. Otherwise, it does not occur. Okay? We only know this once we perform the experiment, meaning that once we know omega itself. We know A itself from scratch, from the beginning. We know A as a set. We just don't know if omega falls into this part or this part. That's the only difference. Okay? Maybe we should see it in examples. Any questions so far about the philosophical meanings of events and so on? Okay, maybe we should discuss some examples now. So yeah, as I said, the simplest example is again by throwing a die. So as you remember, we had a sample space. One of the sample spaces we could choose was 1, 2, 3, 4, 5, 6, right? The face that we see when we throw the die. And now let's give an example of an event. So let's say A is the event that we see a prime number. This is the statement, the informal one. Okay? Now, what is the mathematical or formal one? What is A? A must be a subset of omega, so you should list me the outcomes that are prime numbers, right? So what are they? 2, 3, 5. Thank you. And the complement is just the non-primes, 146. I don't remember the name for non-prime. Anybody remembers? Mathematicians? No? Anyway, not a crucial point. Okay, so maybe another simple example, more continuous one. Let's say you have some bottle of milk. Filled with milk, right? This is in your fridge. You leave your apartment to attend the lecture, but your housemate or roommate is still there to drink some of it. At the end of the day, you're back, you're tired, full of mathematics and probability, and you want to drink some milk. Maybe some of it is just drunk by your friend, right? Who knows? So, and since your friend just left the apartment, he or she didn't say anything to you. So when you get to the apartment, you have no idea about how much milk is left in the bottle. So you have to open the fridge and see. So this is performing the experiment. You open the door, the fridge, and you have to see. You have to see. And at that point, you're performing a random experiment. So once you see how much milk is left in the bottle, wait for 8 hours with the bottle available to your friend. So now you perform the random experiment and see how much milk is left. Let's say this was 1 liter, okay? 1 liter. So now this is omega liters. Maybe it is 0.2 liters now. So your sample space is what? What is your outcome? 0 and 1, right? 0 means that your friend just had all of it. Unfortunately, this is a possible outcome. And 1 is the best case. Your friend also had some lectures and didn't have the time to drink your milk. So that's it. And now what is an event? Let's say A is the event that you have more than half the bottle. So this corresponds to an interval like 1/2 to 1, right? This is an uncountable set. Okay. I have to give an example for my taste, which is from finance, okay? So let's say you have you observe stock prices. So observe the price of a stock during a day. So let's say that's 0, that is 1, this is time, and this is the stock price. If you want strictly more, let's make it strictly more. You have strictly more, which will become a parenthesis like this. Okay, thank you. Okay. So first of all, let's before even talking about an event, let's give a description of the sample space. Well, the stock price fluctuates a lot during the day, so it will follow a path like this. let's say it starts from somewhere that you know, or maybe even you don't know anyway. So it fluctuates like this and finishes the day somewhere, like here. So if you're interested in the behavior of the price during the day, if this is what you're interested in, you shouldn't just look at the final price. You should look at the whole path. Okay? You should look at the whole path. And what is the property of this path? It's a function, right? It's a function from 0, 1 to positive numbers, positive reals. So an outcome is a function. Since it's an outcome, I denote it by omega. From 0, 1 to, I'm writing r plus, which is the interval 0 to infinity. Let's include 0, okay? Not very realistic maybe, but let's include 0. Negative prices are not very reasonable for most cases. So it's a function, but we should also assume it's a continuous function. Although there are models including jumps, let's just say there are fluctuations, but the path is still continuous. The path is rough, but it is continuous. So it's just a continuous function. So now our omega is just the set of all functions from 0, 1 to r plus that are, so omega is a continuous function. And now what is an event? Maybe we are interested in the event that, let's say, this is 3, and this is 5. Maybe we are interested in the event that, so event is the stock price, the price hits the level 5 at least once. In other words, you have this level. For this outcome, for this particular omega, it really hits 5, even multiple times. So omega is an element of A, right? But if I need to write down A mathematically, I should write omega is in omega such that omega t is 5 for some t between 0 and 1. At least one t. And in this picture, omega is in A. Questions about these examples? So we have seen sample spaces and events and outcomes. So the next thing would be the next natural thing to do would be to define probabilities, right? Probabilities of events. So if you are defining a probability, this means you have to tell what the probability of each event is. So you need, indeed, a probability, indeed, is a function on the set of events, right? So the next natural task define probability as a function on the set of all events. What is the set of all events? Well, if an event is a subset of omega, the set of all events would be what? The power set of omega, right? Meaning that the set of all subsets of omega. So, set of all subsets of omega, or the power set of omega. This we denote by 2 to power omega, which just means all subsets, right? So if you have a finite set, empty set is a subset, itself is a subset, singletons are subsets of a finite set, and there are many other subsets, right? But for infinite sets, especially in the uncountable sets, uncountable case, so especially when omega is an uncountable set, 2 to omega, the power set, is too big as the right collection of all events. It is usually too rich, too big. What do I mean by too big? Well, first of all, there is a mathematical inconvenience, which I'm not going to talk about now. And there is also the issue that this has some non-interesting events or uninteresting events. What do I mean by that? Well, if you're doing a random experiment in this room, let's say you're interested in the schools that the students come from, their backgrounds, their research interests, etc., you wouldn't be very interested in the condition of this chair, right? So events about the condition of this chair are not very interesting for you. Or the amount of water left in my bottle is not very interesting for this random experiment. So having everything, having all the events, or choosing the power set of omega as the collection of events is not a very good idea in general. So this is the intuitive reason, and there is a mathematical reason I'm going to mention later, okay? So that's why we restrict ourselves, restrict from 2 to omega to a smaller collection say F. So what is F? F is a collection of subsets of omega. It could be the power set itself, but it could be less than that. And in many experiments, it will be less than that. So the question is, the philosophical question is, what properties should F satisfy? So as a collection of events, what properties should it satisfy? Well, first of all, it should contain the sample space itself. Sample space itself is a subset of the sample space, so it should count as an event, right? Because omega corresponds to the statement, something happens. So something happens is always a true statement. statement. So it should always be counted as an event. Because this corresponds to the statement, something happens. What else? Well, yes, nothing happens. Okay, so this is nothing happens. Great. And what is the relationship between these two? They are the complements of each other. So can we generalize this statement to something like this? If you have an event that is interesting for you, its complement, its negative, is also interesting for you. So some statement, let's say A happens, that statement, or let me say, the negative of this statement happens. So if the statement happens, you know that the negative of that does not happen. And since you say it does not happen, this means this question, the negative of this statement, is also interesting. It's equally interesting for you. So if you include A in your collection of interesting events, you should also include the complement. Okay? They are equally interesting for you. If you can answer one question, you can answer the other in a positive or negative way. Final thing before we go. You have a statement, another statement. Okay. I have a prime number. I have an odd number. Do I have a prime or odd number? Do I have a prime and odd number? Things like this are also interesting for me. If the statements about A and B are interesting for me, their union, so A or B, is also interesting for me. A and B is also interesting for me. Again, if you remember our definition of event, so in the informal version, I have or and and. This is like the statements that I'm talking about here. In the mathematical version, I have union and intersection, which corresponds to or and and, right? So if I have two statements that are interesting for me, their joint statements with or and and are also interesting for me, okay? So in other words, if I have to define a collection of events that is smaller than the power set, choose whatever collection you want, but make sure it satisfies 1, 2, 3, 4. This we're going to call a sigma algebra next time. Thank you.